All right, guys, so coming on to our next video, a cumulative density function. So running through a cumulative distribution function, or a CDF, of a probability density function. Just be really careful with your CDFs and your PDFs. The PDF is the probability density function. It tells us how to find the probability of the scores. A CDF is something slightly different, but it helps along the same lines. Is a cumulative distribution function of a PDF is a function. I'm just going to pause there. A CDF is a function. Because the CDF is a function, we need to be able to input something into that function to get something back out, one unique value. So remember that a CDF, it's a function, right? It's a function that counts, right? That word cumulative means to gather up, collect all of them together. So it counts the total of the area, right? Counts the total of the area under a PDF, under the probability density function, starting at the lowest possible value of x, starting at that lower end of our bound. So when we are finding a CDF, the whole idea is we're not finding a single answer. We're not integrating an area under a curve to get a single value. What we want to do is we want to, how do we estimate the area under the curve given any x value that we want to use that was within the range of our PDF. And what I mean by that is, let's come up here onto the right here. I've got some random PDF drawn, and this is some function, but I'm only interested between values of a and b. And what we would do when we find a CDF of this function, it tells us the area under the curve from that point in time and all the way to the left of it, all the way down to the lower boundary. So if I wanted to pick this point here on the curve, initially, when I find my CDF and put that x value in, let's call it x1, I don't know what it is, but call it x1. When I evaluate that CDF function that I get at that point, it tells me all the area from that point in time down to the lowest boundary. Very similar to what we saw with our normal distribution. Remember when we saw our normal distribution? There was that really messy PDF that gave us a normal distribution. It had ease with fractions and pi and ease to a power. And when we looked at it, we said, there's no way in the world we want to try and integrate that. But we can do it with approximation, trapezoidal rule. We looked at doing it with trapezoidal rule. And after you did it with trapezoidal rule, I gave you a set of tables. In the back of that booklet, you have a set of tables that gave you different x scores. They gave you different one of these. And for each one of those points you looked up on the table, it gave you the area from it all the way down. That was cool with a normal distribution. It's too hard to integrate, so we gave you a table to look up. But let's take that idea further. Well, how do we do that? How did we get those numbers from those tables? Well, we integrate and we find the point. You know, the next time you might be asked to find, you know, the area under this point. So then once you found your CDF, you put that next value in and it tells you all of that area. And remembering also with z-scores, what happens if I want to know what's above? What happens if I want to know something that's above that? Well, then if it's above that, I can do 1 minus the area. Because remember, it has to sum up to 1. So those are those ideas, and this is where we're getting at. We've gone from normal distribution, where here's the table, look up how to find the area under the curve, because it's too hard to integrate, to, well, let's actually integrate it. So that's the idea of what we're doing. We want to get a function out at the end of this so I can keep picking any spot of x that I need instead of having to constantly go back and integrate every single time. Just a couple of bits of notation. The cumulative distribution function, it's capital F of x. The PDF is lowercase f of x. The CDF, capital F of x. from the lowest boundary, A, to some point T, right? We choose T because we want to see a substitution. When you're doing your integration, we want to see you substitute a value in for your integration. So between T of your function with respect to X, okay? And because you're substituting with respect to T, at the end of it, what you're going to get is you're going to get an equation. You're not going to get a single value, you're going to get an equation. And that equation then allows you to input any X value, any point between A and B, and find the area under the curve that you're looking for. All right? Instead of constantly going, oh, now I want from here to here, I've got to integrate between X1 and A. Oh, now I need to between X2 and A. Two forms of integration. Instead of having to do that, this is an equation that gives us straight to it. So let's look at an example. This is worked example 12 from your booklet, and we're given a probability density function, the PDF. Notice lowercase f of x is equal to 4x cubed over 255 for values of x between 1 and 4. Find the cumulative distribution function, or evaluate find the function of the CDF. Well, to find the function of the CDF, what we're going to do is we need to evaluate that between the lowest boundary, which is 1, and some value t, which is going to be our point that can move up and down wherever we want it to be of our function. So what we need to do here is f of x, capital F of x, is equal to the integral between our lower boundary 1 and some upper value t for 4x cubed on 255 with respect to x. Okay, I'm going to factor out our constant out of here. So what I'm going to do, I'm just going to take the fraction out. 1 on 255 outside the integral between t and 1 of 4x cubed with respect to x. Adding 1 to the power, 4x cubed plus 1 becomes to the power 4. So it's x to the power 4. And I've then got to divide that by 4. So 4x to the power 4 over 4 just becomes x to the power of 4. So we now have 1 over 255 outside of x to the power 4 evaluated between t and 1. Which, if we go through and finish that off, it's 1 on 255 outside of t to the power of 4, putting our substitution in, minus 1 to the power of 4, which we end up with, that's our function. What we now need to do is look, can we simplify this algebra anywhere if there needs to be? Well, if I have a look at this, this algebra is already now simplified. So coming up here, what we have now is capital F of x is equal to 0 for values of x less than 1. We don't want to add any area up less than 1. It is equal to 1 on 255 outside of x to the power 4 minus 1 for values of x. Rub this out. Sorry guys, for values of, for 1x 4, for values of x between 1 and 4, and it is 1 for values of x that are greater than 4. And remember that this whole idea of a CDF, a cumulative distribution function, is to add up all of the areas under the curve. Now remember, under the point of the curve, between 1 and 4, it has to add to 1. So if I'm because it's a probability density function, if I'm adding all of the areas between 1 and 4, this up to 4, it needs to add together to give 1. After the number 4, I don't care. I don't want to add any more area. So I know it's 0 area after 4. But because up until the point 4, I've already added all my areas together, every single point after 4, the total area will be 1 because I've already added to 1 up here. And that's how we find our CDF. We write it as a capital F of X, 0 before our lower boundary, our function between our boundaries, and we know this function is going to total together to 1 at the top, so everything after our upper boundary, it must add together to give 1. What we're going to go on to next is and have a quick look as, well, what happens if this is a piecewise function? What happens if our PDF is from a piecewise function? So we're going to go through and quickly look at that. And in the last video, what we're going to look at is, well, what's the point of having a CDF? What's the point? How does it help us? And we'll get through that later. Cheers, guys.